Wait.
Hello, good morning everyone. Am I audible? Good morning everyone. Am I audible? Hello. अरे join करके Hello, am I audible? आ रहा है सर आवाज? चल रहा है इसमें तो ये नहीं है ये नहीं है सर व्हाट्सएप पे सेंड करो सबको एक बार कौन सा हाँ ये वाला ये हेलो गुड मॉर्निंग एम आई ऑडिबल ठीक so today we will start our next topic that is okay we will wait for 2 more minutes let everyone join. Morning everyone. Let me start our today's topic, that is apparent depth of a liquid. Apparent depth of a liquid in a water tank. So consider this is our water tank and water is filled up to a height HR. What is HR? HR is the real height. HR is the real depth, or we can say depth. HR is the real depth of the water in the tank. So if a person see from here, if a person observe from here directly above this point O, then from this point the ray will incident on the interface normally. So if ray incident normally, then it will not change its path. It will not change its path as we discussed yesterday. So it will not change its path. It will go directly to the observer. But if the ray is incident, but if the ray is incident at this point, consider this point is P. So this is oblique incidence. If this oblique incident, then we draw a normal. So this dotted line N, it is the normal. In this case, it is the normal. So this is the incident ray OP, and this dotted line is the normal. So the angle between OP incident ray and normal, it is called the angle of incidence. This is denoted by I. So this water is denser medium, and above the water there is air present, and the air is rarer medium. So now the light is going from denser medium to rarer medium. So if ray is going from denser to rarer, then it will bend away from the normal. It will bend away from the normal. So this is normal and this is a refracted ray. So the angle between normal and refracted ray, it is angle of refraction. So this angle is angle of incidence. So this angle is also angle I. This is the alternate angle. Okay, this is the alternate angle. And this angle is R. So this angle will also be R. Now, if we retrace this ray backward, then it will meet at O dash. It will meet at O dash. So if a person look from here, then he will see the bottom at O dash instead of O. Instead of O. So this from the interface up to the point O dash, this is the apparent depth. This is the apparent depth. And this depth we have to calculate. So we will apply the Snell's law as we discussed yesterday. This is the Snell's law. If we apply Snell's law at this point, at P point, then what we will write? The refractive index of denser medium, it is mu p upon the refractive index of rarer medium, that is mu a, it will be equal to sin r upon sin I. This is the Snell's law that we discussed yesterday. Okay, so this is the Snell's law. Now we have to find the value of sin r and sin I. We have to find the value of sin r and sin I. So sin r we will calculate from this triangle O dash, and consider this point is P dash. So we will calculate from the triangle O dash, P dash and P. From this triangle we will calculate the value of sin r. So what is sin r? Sin r is equal to perpendicular. This angle is 90 degree on the interface. So perpendicular is O dash, P dash upon hypotenuse. What is hypotenuse? O dash P. This is O dash P. This is sin r. Similarly, now we will calculate the value of sin I. What is sin I? Sin I we will calculate from the triangle O, P dash and P. O, P dash and P. So from this triangle O, P dash and P, sin I is equal to, we will get perpendicular. Perpendicular is OP dash upon hypotenuse. What is hypotenuse? It is OP. No, sorry. Perpendicular is PP dash. Perpendicular is PP dash. So we write here P. PP dash. This is the perpendicular. PP dash. Similarly, here perpendicular is PP dash. Okay, perpendicular is PP dash and hypotenuse is, it is OP. So this is sin I and this is sin R. If we put these values here, sin R upon sin I, then this perpendicular PP dash, PP dash, both will cancel. Both will cancel, and what we will get in HR upon HA. HR is the real depth, and HA is the apparent depth. So this is the formula. You can also remember this formula as apparent depth upon real depth, or as given in the question, real depth upon apparent depth. It is equal to mu B upon mu A. Mu B is the refractive index of the medium from which light is coming. Mu B is the refractive index of the medium from which light is coming. Light is coming from denser medium, and mu A is the refractive index of the medium in which light is going. So mu A is the refractive index of rarer medium. Here object can be present in any medium. It can be present in rarer medium, or it can be present in denser medium. So you have to remember that mu B is the refractive index of the medium from where light is coming, and mu is the refractive index of the medium in which light is going, instead of rarer or denser. So this is the apparent depth. Now apparent shift. What is the apparent shift? This is the apparent depth, and this is the real depth. So what is the shift in the height? This O dash is the shift. This is the shift. So how we can calculate it? HR minus HA. HR is the real depth, and HA is the apparent depth. So we can calculate HR minus HA. HR minus HA. What is HA? We can write from here HR by mu, and this is the apparent depth shift. Shift means by this distance the object will appear to be raised. By this height the object will appear to be raised. Now next is TIR, total internal reflection. So what is TIR? It is the phenomenon of reflection of light back into the same medium. It is the phenomenon of reflection of light back into the same medium. If when this reflection occurs, okay. So what is TIR? TIR is the phenomenon of reflection of light into the same medium from this interface of denser and rarer medium. So here, if this is the object, this medium is a denser medium. This medium is denser medium. It can be water, glass, or anything. This medium is denser medium. This medium is 1 minute, 1 minute, na 1 minute. Everyone can join, na? It is open for all. Open for all. Okay, so this is the object present in the denser medium. So for TIR, there is a condition that is object must be present in denser medium. In apparent depth or real depth, this was not the condition. But in TIR, object must be present in the denser medium. So this is the object which is present in the denser medium. Consider here the denser medium is glass. So refractive index of glass is mu G. And above this glass, there is rarer medium. Above this, there is rarer medium. The refractive index of rarer medium is mu A. The refractive index of rarer medium is mu A. Okay. So if light incident normally on the interface, then it will pass straight, normal, without deviation, without any refraction. Now, if light incident on the surface here at this point, then it will go from denser to rarer. So it will bend away from the normal. So this is the angle of incidence. Now again, if we increase the angle of incidence, if we again increase the angle of incidence, then again refraction occur. Light will go. Now we increase the angle of incidence again. Then at this value of IC means critical angle. If we continue increase the angle of incidence, then at a one stage, this angle of incidence will become equal to critical angle. What is critical angle? Critical angle is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium becomes 90 degree. It is, am I audible? Am I audible or not? Please confirm. Chandeep Gogoi sir. Confirm sir, audible or not? Okay. So if angle of incidence becomes equal to critical angle, then for this angle of refraction in rarer medium is 90 degree. Now again we are increasing the angle of incidence. So for this angle of incidence become equal to this critical angle. So if angle of incidence becomes greater than critical angle, then this surface will start act as a mirror. This surface will start act as a mirror. And if this is a mirror, then light will not go in the rarer medium. It will bounce back into the denser medium. So this surface act as a mirror and this is a reflection. So for this angle will also be equal to angle of incidence, because law of reflection, what is law of reflection? Angle of incidence and angle of reflection both are equal. So these both angles are equal to angle I, angle of incidence. So these are the two conditions for TIR. One is object must be present in the denser medium, and second, the angle of incidence in the denser medium must be greater than critical angle. And what is the critical angle? Critical angle is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree. Now we can apply here Snell's law. Consider this point is P. So apply Snell's law at P. Snell's law at P. If we apply Snell's law at P, then it means the medium below the point P is denser medium. Refractive index is mu g. Angle of incidence is sine I equals to above the point P, there is a rarer medium, air of refractive index consider 1, and angle of refraction is 90 degree, sine 90 degree, critical angle for critical angle. So this sine I angle of incidence is angle of critical angle. So sine C is equal to sine 90. Sine 90 is 1 upon mu g. Upon mu g. I write it here. Sine C equals to 1 by mu g. This is the formula that we will use to calculate the critical angle. 1 by mu g. 1 is the refractive index of rarer medium and mu g is the refractive index of denser medium. So you can remember this equation by this, that in the numerator we will write the refractive index of rarer medium and in denominator there will be large refractive index means of denser medium. So this is the formula we will use to calculate the critical angle. This is the same derivation that we did here in the last slide. So these are the some applications of TIR. Looming is the application. Looming means in cold water, if we go with height, then temperature increases. Okay. Similarly, mirage. Mirage means in the desert, in hot days, there is a, we see some water in desert and also on the road. This is called mirage. Mirage is an optical illusion. Mirage is an optical illusion. This occurred due to TIR. Similarly, next application is optical fiber. This is important application. Next is optical fiber. Optical fiber are used in many things and technology nowadays. In medicines also we use it. We use in transmission of signals. Okay, so it is made of, first material is core. First material is core. The inner layer is made of core. Is core, and the outside the core, the material is called cladding, and on the surface this is called buffer. Buffer, or we can call it, it is a coating of plastic, rubber. This is a coating. Okay, so optical fiber are fabricated with high quality composite glass quartz fiber. These are made of glass or quartz fiber. Each consists of a core, cladding. Each consists of a core and a cladding. The refractive index of the core is higher than that of the cladding. Why the refractive index of core is higher? Because to occur TIR. When TIR can occur? If angle of incidence is greater than critical angle. So for this condition to satisfy, the refractive index of core must be greater than the refractive index of cladding. In optical fiber, there is no much loss of energy. There is no much loss of energy, intensity, or signal of energy. So we use it. In this, we can see this diagram. This outer layer is cladding. This has low refractive index. And this inner layer is core. This has high refractive index. It has high refractive index. So from this end, from this left end, light incident on this pipe, optical fiber pipe, a bundle of optical fiber is also called a light pipe. So here refraction will occur because outside is rarer medium and inside is denser medium. So refraction will occur and light will go in the in this optical fiber. So at this surface of core and cladding, the TIR occur, and the TIR occur and light will again reflect into the same medium, because here angle of incidence is greater than critical angle. Similarly, again here TIR occur and signal will pass through the opposite end. So this is the application of TIR. It is used in signals, transmission, receiving signals. Okay, so this is the question on TIR. If the critical angle for a certain medium and vacuum is 30 degree, medium and vacuum, as you know, TIR will occur if the object is present into the denser medium. So critical angle for medium and vacuum is 30 degree. You have to find the velocity of light in that medium. Velocity of light in that medium. So critical angle is 30 degree. We have to find the velocity of light. Vacuum, one medium is vacuum and other is some any other medium. Okay, so we'll apply the formula of critical angle. What is the formula? Sin C equal to, in numerator we will write the refractive index of a rarer medium. And what is rarer medium? It is vacuum. So refractive index of vacuum we can take a 1 upon refractive index of a denser medium. In denominator we will write the refractive index of a denser medium. So for denser medium, refractive index is consider mu. So sin C equals to 1 by mu. So from here mu equals to 1 by sin C. And what is the value of C? It is 30 degree. Value of C is 30 degree. So mu equals to 1 by sin 30. What is sin 30? It is 1 by 2. So 2 will go in the numerator. So refractive index of a medium is 2. So we find the refractive index. So we have to calculate the velocity. And we know, as we studied yesterday, that refractive index mu equals to c by v. It means v equals to c by mu. So c is speed of light. So speed of light is equal to 3 into 10 raised to power 8. Speed of light is equal to 3 into 10 raised to power 8 upon mu. Mu is the refractive index, it is 2. So speed is equal to 3 by 2. 3 by 2 means 1.5 into 10 raised to power 8 meter per second. This is the speed of light in the medium. Okay, so if you have any problem, then you can ask. So let us continue. Then spherical refracting surface. Spherical refracting surface. This is easy portion. You can do it by yourself also. Spherical refracting surface. It is a part of a sphere. It is a part of a sphere of refracting material. A surface which is convex towards the rarer medium, it is called convex refracting surface. Convex spherical refracting surface. This part is convex towards the rarer medium. Rarer medium means this is the rarer medium. This is the rarer medium. So this portion is convex towards the rarer medium. So it is convex spherical refracting surface. And this medium is concave towards the rarer medium. So it is the concave spherical refracting surface. This point is the center of curvature of this spherical surface, and this point is the pole. The distance from pole to center is r. R is the radius of curvature. Similarly, in concave spherical refracting surface. This is also the application of TIR prism. Okay, this is also the application of TIR that was left there. TIR, this is the isosceles glass prism. This can turn the object by 90 degree and 180 degree. It can turn the object by 90 and 180 degree. So if we take this prism in this shape, then consider AB is the object. Then from A and B, top and bottom of the object, ray will incident on this surface. Consider this surface is P, Q, and this point is R. So ray will incident on the surface PQ. If ray incident on the surface PQ, then rays are falling normally. Rays are falling normally. So if ray fall normal, then we study yesterday, they will not change their path. They will go straight. So they incident on this face. They incident on this face at an angle 45 degree. So their TIR will occur. Why? Because they are incident at an angle for which angle of incidence is greater than critical angle. Greater than critical angle. How we can calculate the critical angle? By the formula sin C equals to 1 by mu. And the refractive index of glass is 1.5. So we can calculate. So here TIR will occur. So they will come into the same medium. And why at this in this direction at this angle? Because again law of reflection. If TIR occur, it means law of reflection. So both angle of incidence and angle of reflection will be equal. So they will come into the same medium. And here they will form the image. So this prism turn the object by 90 degree. By 90 degree. Similarly, here in the second case, this is the object AB. Ray will incident on this face. Consider this face is PQ and this point is R. So here on PQ, rays incident normally. So if they incident normally, then they will go undeviated without refraction straight. So here they will incident, and here again angle of incidence is greater than critical angle. So they will come again into the same medium at an angle of reflection equal to angle of incidence. So at this surface, again they fall, again TIR occur, and they will reflect into the same medium. At this face, they fall normally, so they will pass straight. Okay, so this is the required image. So object is upright and image is downside. So this is 180 degree. This rotate by 180 degree.
So this is the application of a TIR. Next, we are studying the spherical refracting surface. We are studying spherical refracting surface. So there are some assumptions and sign convention for these spherical refracting surface. Assumptions. What is the assumption? Object is the point object lying on the principal axis. Object must be the point object. Okay. In mirror formula, lens formula, we will take the object extended object. But in spherical refracting surface, you will see the object is always point object that will lie on the principal axis. Second, incident and refracted ray make small angle with the principal axis. As we discussed yesterday, in this chapter in our 12th class course, the most of ray that we discuss are para-axial rays. The rays are para-axial ray, and if para-axial rays are there, then they will make the small angle with the principal axis, and also aperture is small. And third is also the aperture is small. For para-axial rays, angle is small, aperture is small. So these are the assumptions, and this is the Cartesian sign convention. What is the sign convention? Incident ray is taken from left to right, means if we measure the distance in the direction of incidence ray, that is positive, opposite is negative. Second, these are almost same that we discussed yesterday. All the distance are measured from pole, pole of the refracting surface. Okay. The third is same incidence ray direction, that we will take positive, and opposite that we will take a negative. The vertical distance measured from principal axis in upward direction. We discussed yesterday also, these vertical distance we will take a positive, and the downward distance we will take a negative. These downward distance we will take a negative. Okay, so these are the sign convention and some assumptions. Assumption is object is point object, angle is theta small because rays are paraxial. So now refraction, these are the spherical refracting surface. These are the spherical refracting surface. Okay, so in almost all refracting surface, the derivation is similar, same. So we will do for one, and other rest are almost same. Okay, so refraction at convex surface. This is the convex spherical refracting surface because its convex part is towards the rarer medium. Its convex part is towards the rarer medium. So here real image is formed. Here real image is formed. As we discuss in case of mirror, in case of mirror, either it is concave mirror or convex mirror. If both object and image are on the same side, that image is called real image. And if both object and image are on the opposite side of the mirror, that is called virtual mirror. That is called virtual image. But in case of refracting surface, and same for lens, this is opposite of the mirror. Here, if object and image both are on the opposite side, both are on the opposite side, then this is called real image. And if both are on the same side, then this is called the virtual image. Okay. So now we are taking refraction from rarer medium to denser medium. We are taking refraction from rarer to denser medium. Rarer to denser medium and denser to rarer medium. Rare to denser medium means object must be present in the rarer medium. Rarer to denser means object must be present in the rarer medium, and denser to rarer means object must be present in the denser medium. Object must be present in the denser medium. So this is the object. O is the object, as we study in the assumption that object must be point object that will lie on the principal axis. So this is the object. From the object, one ray incident on the surface normally. So it will pass straight, and other ray is incident on the surface at this point A. So OA is the incident ray. So here we will draw the normal. So this dotted line is the normal which is meeting at the center of a curvature. So the angle between incident ray and normal, this angle is called angle of incidence. This angle is called angle of incidence. So now this is the rarer medium and this is the denser medium. So light is going from rarer to denser. So it will bend towards the normal. So this light will bend towards the normal. So this straight line which is coming direct from pole and this refracted ray both will meet at I and here image will form at I. Okay. So now here you have to remember that either it is convex spherical surface, concave, real image, virtual image. The object form the angle we are denoting by alpha. Image form the angle with the principal axis we will denote by beta. And normal forms the angle at principal axis that we will denote it by gamma. And this is the normal and this is the refracted ray. So the angle between normal and refracted ray is R. R is the angle of a refraction. R is the angle of a refraction. So here this is tan alpha. This is tan alpha. Tan alpha means this angle. We draw here this perpendicular. This is the perpendicular line. From point A, we draw a perpendicular on the principal axis. We draw a perpendicular on the principal axis AM. AM is the perpendicular. This is the object. So the distance from pole to object, this distance is denoted by U, object distance. The distance from pole to image, this is denoted by V, image distance. And the distance from pole to center, this is denoted by R, radius of curvature. Rarer medium has a refractive index mu1 and denser medium has a refractive index mu2. Denser medium has a refractive index mu2. So first of all, we will write this Snell's law. First of all, we will write this Snell's law. So what is Snell's law? We will apply Snell's law at A. We will apply Snell's law at point A. Okay, so we will apply Snell's law at A. So what is Snell's law at A? Mu2 upon mu1 equals to sin I upon sin R. This is the Snell's law that we discussed yesterday. So in the assumption, we assume that the angle made with the principal axis are small. So from this Snell's law, we can write this sin I as I and this sin R as R equal to mu2 by mu1. Now cross multiply these. So I into mu1, it is equal to mu2 into R. This is the Snell's law. Now here we have to calculate the value of I. I means angle of incidence and R means angle of refraction. We have to calculate the value of I and the value of R and we will put the value in this equation. Okay. So for this value of I and R, we will take a tan alpha, tan beta, these we will take. So from here, we can write these also, or there is no need to write this. Na? Why? Because this is the angle I. This is the angle I at A. And this is the angle alpha. This is the angle alpha and this is the angle gamma. Okay. So look at the triangle AOC. Triangle AOC. This is the triangle AOC. In this triangle AOC, as you see, alpha and gamma. Alpha and gamma are the interior angle of the triangle and angle I is the exterior angle of the triangle. This is the exterior angle of triangle and we know this sum of the this exterior angle of the triangle is equal to the sum of the two internal opposite angle. So we can write directly I equals to alpha plus gamma as it is written here. I equals to alpha plus gamma because I is the exterior angle and alpha and gamma are the interior angle. Similarly, for angle of refraction, we can take this triangle. This is beta, this is R, this is gamma. Okay. Let me clear this. This is beta, this is gamma, this is R. So look at the triangle ACI. Look at the triangle ACI. In this triangle ACI, R and beta are the interior angle of the triangle. R and beta are the interior angle of the triangle, and gamma is the exterior angle. Gamma is the exterior angle. So this exterior angle gamma will be equal to sum of the two interior opposite angles. Opposite angles are R and beta. So we can write gamma equals to R plus beta. So from here we can write R equals to gamma minus beta. This is the R equals to gamma minus beta, and this is I equal to alpha plus gamma. Now we will put these in this equation here. We will put these in this equation. So mu1 I, what is I? I is alpha plus gamma equals to mu2 R. What is R? Gamma minus beta. This is gamma minus beta. So we will solve this alpha. What is alpha here? This is the alpha. So now we will use this perpendicular. This is the perpendicular. We will use this perpendicular. We can write alpha as am upon mo. So we can write this as am upon mo plus gamma. What is gamma? Gamma is this angle. This angle. So we can write gamma as am upon mc, as angle equal to arc by radius. So we can write am upon mc, and the aperture is here small. It is equal to mu2 into gamma minus beta. Again gamma is am upon mc minus beta. Beta is this. So it is am upon mi. Beta means image. Image is mi. So am upon mi. So on both sides we can cancel this am. On both sides we can cancel this am. So what remains? What remain here? Mu1 into 1 upon mo. Mo. What is mo? This is m, this is o. Okay, and this aperture, we know this aperture is small. If this aperture is small, then we can assume this m and p are very close to each other. This m and p are very close to each other. If these are close, then we can write this mo as equal to po. We can write this as equal to po plus 1 by mc. Again, m is close to p, so mc we can write pc. It is equal to mu2 into 1 by mc, means 1 by pc, then minus 1 by mi. Mi means pi. Okay, now mu1 into 1 upon po. Po means pole, p means pole, o means object. So from pole to object, this distance, according to sign convention, this distance is minus u. So we can write minus 1 by u plus 1 by pc. P means pole, c is center of curvature. So from pole to center of curvature, this is the radius of curvature. So according to sign convention, this distance is positive. So equals to mu2 into 1 by pc, pole to center, this is again r, minus 1 by pi. Pi means pole to image. So according to sign convention, pole to image, this is positive. So minus 1 by v. So minus 1 by v. So we reach here. This is the step. Na? We reach here. Now what we will do? We will multiply mu1 and mu2 both sides. We will multiply them and open the bracket, and we will rearrange. If we rearrange, then we will get this equation. Minus mu1 by u plus mu2 by v equal to mu2 minus mu1 by r. This is the formula for rarer medium to denser medium. This is the formula for rarer medium to denser medium. Either it is convex surface, concave surface, real image, virtual image. In all case, this formula will be similar. And from denser to rarer medium, and from denser to rarer medium, what will be the change in this formula? In this formula only, we will replace this subscript. Where 1 is written, there we will write 2, and where 2 is written, there we will write 1. For example, here rarer to denser. What is rarer to denser? Minus mu1 by u plus mu2 by v equals to mu2 minus mu1 by r. This is from rarer to denser. So in denser to rarer, we have to simply replace these subscript 1 and 2. So here minus mu 1. Here in place of 1, we will write 2 upon u, plus as it is mu 2. Here in place of 2 we will write 1 upon v equals to mu 2 minus mu 1. So here in place of 2 we will write 1. Here in place of 1 we will write 2 upon r. So this will be the formula for denser to rarer medium. This will be the formula for denser to rarer medium, and this is the formula for rarer to denser. So all equations are almost same. There is change only in the sign convention and the diagram that we draw, and there is no other change. Okay, so now we will start our next topic, that is lens maker formula. Now we will start our next topic, that is lens maker formula. Lens maker formula for convex lens or lens maker formula for concave lens. For both lenses, lens maker formula are similar. Lens maker formula is 1 by f equals to refractive index of lens upon refractive index of surrounding. Surrounding means the medium in which lens is present. The medium in which lens is present. Mu lens upon mu surrounding minus 1 into 1 by r1 minus 1 by r2. 1 by r1 minus 1 by r2. So this is the lens maker's formula. Means the formula which we will use to make a lens. This is the lens maker formula. It is same for both lens. Either it is convex or it is concave. So this lens maker formula, let me derive here this lens maker formula. This is the convex, this is important topic again. Lens maker formula, it is important topic. Either derivation or a numerical will come from this topic in the CBSE exam. So this is the convex lens and this is the principal axis, convex lens, and this is the principal axis. Consider this point is L and this point is L1, and this point, it is called pole. So P1 for this surface, this is P2. Lens is made up of two surface. So one surface like spherical refracting surface. So first surface is L P1 L1 and second surface is L P2 L1. Okay. So consider this is the object. This is the object. So the distance from this center to object, this is denoted by U. Consider this is the object. So one ray from object will pass straight. It will pass through optical center and it will pass straight without any deviation. Now consider the other ray from object incident here on the surface L P1 L1. Ray incident on the surface L P1 L1. So ray is incident on this surface. So at this surface refraction will occur. Refraction will occur. So this is rarer to denser. So refraction will occur. Light will bend towards the normal. So it will meet here. It will meet here. For surface LP1 L1, only for this surface. Only for this surface. This is the image. Consider this is I1. So for this surface LP1 L1, for this surface O is the object and I1 is the image. For this surface O is the object and I1 is the image. But in actual there this surface also present. Which surface? LP2 L1. This surface is also present. But in real this surface LP2 L1 is also present. So here at this surface again refraction will occur. Again refraction will occur and it will bend again. So this is the final image. This ray and this ray, both refracted ray will cut, and where two refracted ray will cut, their image will form. So this is the final image. So if we take this surface LP1 L1, so for this surface O is the object and I1 is the image. And if we take this surface LP2 L1, so for this surface I1 is the virtual object. I1 will start to act as a virtual object and I is the final image. So from optical center to I1, consider this distance is V1, and from optical center to I, consider this distance is V. Okay. Now we have to derive the formula. We have to derive the relation. So simply we have to do, first we will write the equation for rarer medium to denser medium of spherical refracting surface. For first surface LP1 L1, and for second surface directly we will write the equation of a denser medium to rarer medium for second refracting surface LP2 L1, and we will add these equations. Similarly, we will write in case of concave lens, and same in case of convex lens, and same in case of concave lens. So for first surface, rarer to denser. Rarer to denser is, consider refractive index of rarer is mu1, and lens is mu2. So what we will write? Minus mu1 by u. What is u? Object distance. For first surface, object is u, plus mu2 upon v. V is image distance. But for first surface, image is I1, and this distance is denoted by V1. It is equal to mu2 minus mu1 upon r radius of a curvature. For first surface, we can write it as r1 is different radius. So mu2 minus mu1 upon r1. Similarly, for second surface LP2 L1, we will write the equation of denser to rarer. Denser to rarer means simply we will change this subscript. Subscripts means minus as it is mu1. Here mu1, so we will write mu2 upon u. U is object, but for second surface, what is the object? I1 is the object. I1 is the virtual object. So the distance I1 is equal to V1. This is V1 plus mu2. What is mu2? In place of mu2, we will write a mu1 because denser to rarer upon V1. V is the image, but for the second surface, the final image is I. And this image distance for final, it is V. So V equals to, here mu2 minus mu1. Here we will write mu1 minus mu2 upon R2. Okay, so consider this is the first equation, and consider this is the second equation. So now what we will do, we will simply add equation 1 and equation 2. Equation 1 and equation 2. If we add equation 1 and 2, then plus mu2 by V1 minus mu2 by V1. They will cancel. Both will cancel, and minus mu1 by u plus mu1 by v. Mu1 will outside, and 1 by v minus 1 by u. That we can write 1 by f. So when we add, then we will get this relation mu2 upon mu1 minus 1, 1 by r1 minus 1 by r2. You can add these both, and when you will add, you will get this relation. This relation is called lens maker's formula. This relation is called lens maker's formula. Remember here, mu2 is the refractive index of lens medium, and mu1 is the refractive index of surrounding medium in which lens is placed. Mu1 is the refractive index of a surrounding medium in which lens is placed. Similarly, these two equations we will write for concave lens. Okay, similarly, these two equations we will write for concave lens, and we will add these both equations. We will add these both equations. Okay, so you can do that for concave lens. Now here, this is the question. This is the question. Question of this type previously came in CBSE exam. It is the chance that they can this question, this type of question will also come in the upcoming exams. So what is this? A convex lens of refractive index 1.5. This is the convex lens, refractive index 1.5. Focal length in air is given. Focal length in air is given. Calculate the change in its focal length when it is immersed in water of refractive index this 4 by 3. So if we immerse a lens, either it is convex or concave, into any other medium, then its focal length will change. Why its focal length will change? Because focal length of lens depends on refractive index, mu lens upon mu surrounding minus 1. Focal length of lens depends on the refractive index. So if we dip it in a medium, surrounding medium, then its focal length will change. But for mirror, in case of mirror, either it is concave or convex spherical mirror, if we dip them in the any other medium, then the focal length of mirror will not change. Why it will not change? Because as we studied yesterday, the focal length of mirror is r by 2. Focal length of mirror is r by 2. It does not depend on the refractive index. It does not depend on the refractive index. Focal length of mirror does not depend on the refractive index. Okay, so in case of mirror, the focal length will not change if we dip it into any other medium like here water. But in case of lens, its focal length will change. One thing is that. And second is, if we dip any lens into a medium, if we dip any lens into a medium, so consider refractive index of lens is mu L. Refractive index of lens is mu L, and refractive index of any medium is considered mu m, refractive index of medium. And what is the relation between them? Refractive index of lens is greater than refractive index of medium. If refractive index of lens is greater than refractive index of medium, for example, here refractive index of convex lens is 1.5 and refractive index of medium is 4 by 3. So here refractive index of lens is greater than refractive index of a medium. If this is the case, then in this case, the lens, what is the focal length? Here convex lens. So focal length of convex lens is positive. Focal length of convex lens is positive. So the nature of lens will not change. Here the nature of lens will not change. If this is the condition, refractive index of lens is greater than refractive index of medium, then in this case, the nature of lens will not change. Means if lens is convex, then it will remain convex after we dip into other medium. If it is concave, then it will remain concave if we dip into it other medium. Then what will happen? Its focal length will increase. Focal length क्या होगी? Its focal length will increase. And if this is the case, refractive index of lens is less than refractive index of medium. If refractive index of lens is less, then in this case, the nature of lens will change, means convex lens will become concave and concave lens will become convex. Okay, so this is you have to remember. And similarly, we can do this question by the formula. What is the formula? 1 by f. If it is in air, then what is the focal length? 18 centimeter in air. So 1 by 18 equals to, in air, so refractive index of lens is 1.5 upon surrounding. In air, so medium surrounding is 1. Refractive index surrounding is 1. Minus 1, 1 by R1 minus 1 by R2, because radius is not given here. This is the first equation. Now we can write this as 1 by 18 equal to 1.5 minus 1, it is 0.5. 0.5 means it is 1 by 2 into 1 by R1 minus 1 by R2. It is 1 by 2. 1 by R1 minus 1 by R2. This is the first equation. Similarly, for medium, if we dip in medium, then new focal length consider f dash, mu lens. Refractive index of lens is 1.5. 1.5 means 3 by 2 upon refractive index of surrounding is 4 by 3 minus 1, 1 by R1 minus 1 by R2. 1 by R1 minus 1 by R2. We can write this as 3 by 2. This 3 will go in the numerator, 4 in denominator. It will become this minus 1. So 3 into 3, it is 9 upon 2 into 4, 8. 9 by 8 minus 1. Okay. 9 by 8 minus 1. So we can write it as, when we solve, it is 1 by 8. It is 1 by 8. Okay. So what we will get? 1 by f dash equals to 1 by 8 into 1 by r1 minus 1 by r2. Okay. This is the second equation. This is the second equation. So now what we have to do? Now what we have to do? We have to divide equation 1 by equation 2. If we divide both equation, then on left hand side we have 1 by 18 upon 1 by f dash on the second equation. And if we divide 1 and 2, then 1 by r1 minus 1 by r2 will cancel. So on right hand side we have 1 by 2 divide by 1 by 8. Divide by 1 by 8. Okay. So now I am rubbing this, erasing this. So here what we will write, 1 by 18 f dash will go in the numerator. So here 1 by 2 multiply by 8. So 2 4 ja 8. It means f dash is equal to 18 into 4. It is equal to 72 centimeter. Okay. So here sign is positive. Sign is positive means nature of lens does not change. Before it is convex, now it is also convex. But what happened? Its focal length increase. Initially its focal length is 18. Now its focal length, new focal length is 72 centimeter. So if we dip a lens in a medium, if refractive index of lens is greater, then its focal length will not change, mean its nature will not change. Okay. So now we are moving on the next topic. Principal focus. You all know, hai na? This is in come in class 10 also. You studied this second principle. We usually study this second principle focus. If ray incident on the lens parallel to focus, parallel to, sorry, principal axis, then after refraction they will meet at focus. This is the second principal focus. Similarly, in concave lens, if parallel ray to the principal axis incident on the lens, then they will diverge. So convex lens means convergent lens, and concave lens means it is divergent lens. Okay. And this is called principal focus first. Reverse of this, if ray incident on the lens from a point f1, ray incident on the lens from the focus, then after refraction they will go parallel to the principal axis. Similarly, in concave lens, if they incident on the lens in this direction, that if they go further, then they cut at focus, then they will go after refraction parallel. Reverse of this. Okay. So they are reverse to each other. Both are reverse. So this is the principal focus. Okay. So next is lens formula. Lens formula again very similar to the mirror formula. In case of mirror, if both images are on the opposite side, that is called virtual image. But in lens, if both object and image are on the opposite side, that is called real image. This is the difference in lens and mirror image. So here we are studying lens formula for convex lens. Convex lens forms both image real virtual. Okay. And concave lens form only virtual. So lens formula for both lens, either it is convex lens or it is concave lens. Lens formula for both lens are similar. For both lens formula are similar. What is this? 1 by v minus 1 by u equals to 1 by f. So we are deriving for this topic lens formula. Consider object is placed between f1 and 2f1. In case of convex lens, if object is placed beyond f1, from f1 to infinity or at f1, then real image will form. And if object is placed between optical center and f1, first f1 focus, Okay, then virtual image will form. So here object is placed beyond f1. So in this case real image is formed. Real image means one ray will go parallel to principal axis. After refraction it will pass through focus. Second will go from optical center, and we know if ray pass from optical center then it will go undeviate. So both will cut here. So this is the required image. Distance from optical center to object is u. From optical center to image is v. From optical center to focus is f. Similarly, we will take two similar triangles like we did in mirror formula yesterday. One triangle is ABC, A dash, B dash, C. So AB is the object, C is the optical center, A dash, B dash is the image, C is the optical center. So we can write this for these similar triangle. Similarly, we take two triangle MCF2 and A dash B dash F2. What is MC? This point we take M, because we cannot take AB, so we take MC. MC and AB both are equal. So for this triangle, we can write this, and we know this MC is equal to AB. So in place of MC, we can write a AB. So this is the first equation. This is the second equation. As left hand side of both equations are same, so the right hand side will also be same. Now as you know, according to sign convention, we measure all distance from the optical center. So in this equation there is optical center C, in this equation optical center, here also optical center, but here it is B dash F2. So we have to convert it into in terms of C optical center. So this is B dash image and this is F2. So in term of C, we can write it as CB dash minus CF2. So we write here CB dash minus CF2. Now again we will use sign convention. CB, B means object, it is minus U. CB dash means image, it is plus V. CF2 means focus, it is plus F. We will put here and solve, then we will get this equation 1 by V minus 1 by U equals to 1 by F. Okay. So if there is any doubt, till here, then you can ask. So I sent a feedback form. Kindly fill it. Kindly fill this feedback form. In chat box, I send a feedback form. Kindly fill this form. Okay. Now we are moving to our next topic. So lens formula for concave lens. You can derive the lens formula for concave lens. The lens formula for concave lens will also be this similar 1 by V minus 1 by U equals to 1 by F. So then is linear magnification. Magnification is again height of image upon height of object. You can write plus V by U. Plus V by U. In case of mirror, magnification is negative. It is minus V by U. Here positive plus V by U. This is magnification in term of V and F. You can derive this magnification by lens formula 1 by V minus 1 by U equal to 1 by F. What we have to bring? V by U. So multiply both side by V. If you multiply both side by V, then V into 1 by V, 1 minus V by U equals to V by F. So what we will get? V by U equals to 1 minus V by F. Okay. So V by U equals to 1 minus V by F. If you take LCM, then you will get this F minus V by F. Similarly, this in term of U. If you want in term of U, then you multiply by U. Okay. So these are the magnification formula. You have to remember this magnification formula. Next important topic is topic is power of lens. Power of lens. Power, they can also ask in lens maker's formula. If you dip in any other medium, then what is the effect on power? So if focal length increase, then power decrease. Power of lens is the ability to bend a light falling on the lens. Power of a lens is its ability to bend a ray of light falling on it, and it is reciprocal its focal length. Okay. What is power? Power is the ability of a lens. What a convex lens do? Convex lens converge the ray of light. Concave lens diverge. So what is the power? How much they converge, how much they diverge. So if a lens is thick, then it has more power because it converges fast. If a lens has if a lens is thin, then it will converge slowly because it has less power. So a thick lens has more power and a thin lens has less power. And its mathematical formula, all you know, it is a reciprocal of focal length. Unit of power is diopter. Unit of power is diopter. So if focal length is one thing you have to remember, if focal length is in meter, then you will use the formula 1 by f. And if focal length is in centimeter, then you will use the formula 100 by f. In both case, unit of power will be diopter. So a convex lens has positive focal length. If it has positive focal length, it means it has positive power. If a, and a concave lens has negative focal length, it means it has negative power. Now next, this is power of lens, combination of lens. Combination means if you combine two lens, three lens, four lens, then you have to calculate the equivalent focal length. So equivalent focal length is, it is equal to reciprocal of focal length of each lens, and we will add them. This is the formula to calculate equivalent focal length. And equivalent power, simply add their power. Similarly, you can calculate their equivalent magnification, multiply the magnification of each lens. Multiply the magnification of each lens. So this is simple topic. Next, now we come on prism. Prism. This is important topic again, prism. So in case of prism, you all know the basic about the basic of prism. Now this is the prism, and in prism there are two refracting phase. There are two refracting phase, and the angle between these refracting phase, this angle is called angle of a prism. So one ray is incident on the first refracting phase. First refracting phase is AB. So a ray of light is incident on this refracting phase. And this is the normal. N1 is the normal. So this angle is called angle I, angle of incidence. Now this light refract. So it is going from rarer to denser medium. So it will bend towards the normal. Again, it will fall here. It will go from denser to rarer. So it will bend away from the normal. Okay. This angle between normal and incidence, this is angle I. This is called the emergent ray. So normal and emergent ray, angle between them is angle E, angle of emergence. If this ray go along its original path, this dotted line, a prism is not present. And this is the emergent ray. If we trace it back, then both will cut here. So this angle is called delta, angle of deviation. Angle of deviation, by this angle the ray will deviate. And this angle of refraction is R1, and here angle of incidence we also denote by R2. Okay, refractive index of prism is mu, and outside medium is air. So first we have quadrilateral A, P, O, Q. This is the quadrilateral. We know the angles of quadrilateral is 360 degree. Is 360 degree. And N1 and N2 are normal. Then we can write these opposite angles are, sum of these opposite angles are 180 degree. In case of quadrilateral, equilateral. Okay, so A plus O is 180 degree. Similarly, we have this triangle OPQ, this triangle. And we know the sum of the angles, the sum of the interior angle of a triangle is 180 degree. So this angle is R1, this angle is R2, and this is angle This is O, so we denote it by O. So we can write R1 plus R2 plus O is 180 degree. Now from equation 1 and 2, from equation 1 and 2, right hand side is equal, it is 180 degree. So the left hand side will also be equal. What is left hand side? A plus O, and here R1 plus R2 plus O. So angle O will cancel. So A equals to R1 plus R2. This is the equation. A equals to R1 plus R2. Okay. So this is the equation. A equals to R1 plus R2. Now for angle of deviation, we can write in triangle DPQ. This is D, this is P, and this is Q. In this triangle, this is the triangle. Here this angle, what is this angle? This angle is I minus r1, because this complete angle is I. Similarly, this complete angle is I, and this small angle is r1. So this angle remaining is I minus r1. This angle is I minus r1. So we write here I minus r1. Similarly, this angle is E minus R2, because this is R2, this complete is E. So E minus R2. The sum of these angle is equal to delta. Why equal to delta? Because we study in the last topics that exterior angle of a triangle is equal to sum of two internal opposite angles. So exterior DPQ, the exterior of DPQ is delta. It is equal to sum of these angle. So we write I plus E minus common R1 plus R2. In place of R1 plus R2, we can write A. In place of R1 plus R2, we can write here A. So delta equal to I plus E minus A. Similarly, we can write this equation. So this is the angle of deviation, and this relation you have to remember. In this prism, we derive a prism formula, and also for prism formula, we have to calculate the minimum deviation. In case of minimum deviation, this angle I and this angle E both are equal, and this angle R1 and this angle R2 both are equal. And the refracted ray inside the prism is parallel to the base of the prism. The refracted ray inside the prism is equal to the base of the prism. So this is the case of minimum deviation. When deviation is minimum, then I and E are equal and R1, R2 both are equal. So this is the graph here. On y-axis, there is angle of deviation. On x-axis, angle of incidence. So as we increase the angle of incidence, then first angle of deviation decrease. It reach a minimum value. At this minimum value, there is only one value of angle of incidence. As you can see here one value of angle of incidence is this, and one value is this for this curve. Okay, but here there is only one value of angle of incidence. So at minimum deviation, angle I and angle E both are equal. After this minimum deviation, when we increase the angle of incidence, then angle of deviation again start to increase. Okay, and this curve is not symmetrical. This curve is not symmetrical. This is not at the midpoint. This is not symmetrical. This is tilted curve. It is more tilt towards left. Okay, this is not symmetrical curve. So refractive index of material of prism, this is the equation that we derive. Here for minimum deviation, R1, R2 both are equal to R. So we can write 2R equals to A and R equals to A by 2. Similarly, this is the equation that we derive in last slide. So I plus E equals to A plus delta. In case of minimum deviation, I and E both are equal. So I plus I we can write 2I. It is equal to A plus delta minimum. Delta we can write in place of delta minimum. So here I equals to A plus delta minimum upon 2. And this is again the Snell's law. Okay, we can apply Snell's law on the face of prism. This is the prism. Here, this angle is angle of incidence and this angle is angle of refraction. Okay, so here this is the refractive index. When we apply Snell's law, then mu equals to sine I upon sine R. So what is I? I is A plus delta minimum upon 2. What is R? R is A by 2. So mu equals to sine A plus delta minimum upon 2 upon sine A by 2. This is the prism formula. This is called the prism formula. Okay. So next is, there is one formula is also there. For deviation, delta equal to mu minus 1 into A. This formula we will use if angle of prism is less. If angle of prism is less than 10 degree, then to calculate the deviation, we will use the formula delta equals to mu minus 1 into A. Okay. Now we are moving to next slide, dispersion of white light. This topic you also had studied in class 10, dispersion of light. Dispersion of white light means the phenomenon of splitting of white light into its seven color when it falls on a prism, oblique incidence on a prism. So this is the white light incident on the prism. This is the white light incident on the prism. Here it will split into seven colors. That is Vibgyor. Violet is near the bottom, red is at the top. So there is maximum deviation in violet color and minimum deviation in red color. This is the deviation in red color. This is the deviation in violet color. So for violet color, deviation is most, and for red color, deviation is least. For red color, wavelength is maximum. For violet color, wavelength is minimum. Okay, so this is the deviation. नेक्स्ट ब्लू कलर ऑफ स्काई, नो ये कुछ नहीं करना. रेडिश अपीयरेंस. नेक्स्ट टॉपिक इज ऑप्टिकल इंस्ट्रूमेंट्स. नेक्स्ट टॉपिक इज ऑप्टिकल इंस्ट्रूमेंट. ऑप्टिकल इंस्ट्रूमेंट, दिस इज अगेन इंपॉर्टेंट टॉपिक. ऑप्टिकल इंस्ट्रूमेंट. सो फर्स्ट इज सिंपल माइक्रोस्कोप. सिंपल माइक्रोस्कोप और वी कैन कॉल इट ए मैग्नीफाइंग ग्लास. सिंपल माइक्रोस्कोप और वी कैन कॉल इट ए मैग्नीफाइंग ग्लास. इट इज ए मैग्नीफाइंग ग्लास. So we have to find the magnifying power. We have to find the magnifying power. So in simple microscope is made up of one lens. Simple microscope is made up of one convex lens only. So here consider this is the object. This is the object. Okay. So one ray will incident on the lens parallel to the principal axis. After refraction, it will pass through focus. Okay. And second ray will pass through the optical center. So after refraction, it will go straight. And here in simple microscope, we are studying the virtual image. Convex lens, when convex lens forms virtual image, if object is placed between optical center and focus. So here in simple microscope, object is placed between optical center and focus. So it will form the virtual image. In case of lens, virtual image and object both are on the same side. Okay, so they will not meet if they move further. So if we retrace them in back direction, then both will be at here, and here image will form. This is the image. This image in case of magnifying glass, it will form at least distance of distinct vision. That is 25 centimeter for a normal eye. Okay, so this distance is denoted by U object distance, and this image distance, it is denoted by D. What is D? D is the least distance. So we will see from here. We will see from here. If we see from here, then we will see the image. Okay. So magnification, we have to calculate magnification or magnifying power. So what is the formula of magnification? V by U. V by U. So we can write it as V as it is. V as it is. So what remains? 1 by U. From lens formula. What is lens formula? 1 by V minus 1 by U equal to 1 by F. So from here, 1 by U equal to 1 by V minus 1 by F. This is the lens formula. So here in place of 1 by U, we can write V by U as V multiply 1 by U. So in place of 1 by U, we can apply lens formula, that is 1 by V minus 1 by F. Minus 1 by F. Okay. So we will multiply by V, both equation. So first V by V, 1 minus then V by F. So 1 minus V by F. So what is V? V is the image distance. Here image distance, we will measure from optical center in left direction. Incidence ray, right, we will go left. So it is minus D. What is V? Minus D. So 1 minus 1 minus D upon F. So minus minus become plus. So magnifying power is 1 plus D by F. This is the magnifying power or magnification in case of simple microscope. In case of simple microscope or magnifying glass. In simple microscope, there is only one lens, that is called eye lens. That is called eye lens. So here, so it is called, so this is the magnifying power of eye lens. Okay, we can write Fe also because it is for eye lens. Now next is compound microscope. Compound microscope, it consists of two lens. Compound microscope, it consists of two lens. One is called objective lens, one is called eye lens or eyepiece. These both lenses are placed on the end of a tube. These both lenses are placed on the end of a tube. Their their length we can arrange, है ना, their position we can manage, we can arrange. So in this, objective lens has short aperture and eyepiece has large aperture. Compound microscope we use to observe very minute particles, very small particle that we cannot observe from our naked eyes. Okay, that we for these particles, minute particle, we use compound microscope. So here objective lens has short focal length, short aperture. Eye lens has also somehow short focal length, but more than objective, and large aperture. Okay. So this is the object. This is the object for objective lens. U O. U means object. Object distance. O means for objective lens. So this is the object distance for objective lens. Object distance for objective lens. So one ray parallel to principal axis will incident on the lens. After refraction, it will pass through focus and it will incident on the eye lens here. Okay. Similarly, second ray from the optical center will pass undeviated and incident on the eye lens. Both will cut here. Where both will cut, there a inverted image will form, that is denoted by A dash B dash. This is the inverted image. Now this A dash B dash image of objective lens, it will act as a object for the eye lens. So from here, ray incident on the eye lens and they will refract. They will refract. When we trace them in the back direction, then they will cut here. Here they will cut. Okay, this is the least distance. Again, in case of compound microscope, this is the least distance of a distinct vision. So we will join this final image, final position of image to the optical center of eye lens. So this angle is made by image. So this angle is denoted by beta. Again, this is the object. So we will put this object here because from here we cannot draw the lines. Okay. So we take this object here and we meet this line at the eye lens. So this angle made at the eye, it is alpha. This alpha angle is made by the object. We consider object is A triple dash upon A double dash. This angle is alpha and the angle made by image is beta. Okay. So objective, these all are description. Now we have to derive the relation. So what is magnifying power? Magnifying power is beta by alpha. Beta means angle made by image at the eye lens and alpha angle made by object at the eye lens. So angles are small. So we can write 10 beta upon 10 alpha. 10 beta upon 10 alpha. Now 10 beta. 10 beta we will write from here again. 10 beta from this triangle. A double, this is beta. So we can write A double dash, B double dash upon this distance, it is D. Perpendicular upon base. Similarly, 10 alpha, we can write A double dash, A triple dash upon D. Okay, we can write this. So this is 10 beta, this is 10 beta, and this is 10 alpha. If we write in denominator, then numerator they will reverse. So this D and D will cancel. Okay, this D and D will cancel. A double dash, B double dash as it is. A double dash, A triple dash. In place of this, we can write AB because both has the same height. Okay, so A double dash, B double dash upon AB. Now we write here A double dash, B double dash, here AB. Now multiply and divide by A dash, B dash. What is the A dash, B dash? It is the image of objective lens. So A double dash, B double dash upon A dash, B dash. A double dash B double dash upon A dash B dash. It is the image for eye lens. It is the object for eye lens. So image, height of image upon height of a object. Height of image upon height of object. We can write magnifying power of eye lens. A dash B dash is the image for objective lens and AB is the object height for objective lens. So A dash B dash upon AB, we can write MO, magnifying power of objective lens. So ME, what is ME? Magnifying power of eye lens. Magnifying power of eye lens, as we derive in simple microscope, it is 1 plus D by Fe. It is 1 plus D by Fe. And magnifying power for objective lens, it is VO by UO. So we will put here, and this is the required relation. VO upon minus UO, 1 plus D by Fe. We can also assume, this is the assumption, U, object distance for objective lens. As you can see here, as you can see here, this object lies close to FO. So we can write this UO as approximately equal to FO. Similarly, this VO is lies close to eye lens. So we can write this VO approximately equal to L. What is L? L is the length of the tube. So we can write this. So here, this is the same assumption. UO equals to FO and VO equal to approximately L. So we will put here, then here in place of VO, we can write L, and in place of UO, we can write FO. This minus sign is same. So M equals to minus L by FO into 1 plus D by FE. In term of magnitude, it is positive. Okay. In case of normal adjustment means image format infinity. If we derive this, then we simply remove this one, then it is minus L by FO into D by FE. This is the magnifying power. Now for telescope, astronomical telescope, it is we use this for observing the moon, distant object. Okay, very far away object we will use. In this, the objective lens has large aperture, large focal length. The eye lens has short aperture, short focal length. So these are the ray which are coming from the distant object, very far off object. So consider this angle is alpha for object. So this is also alpha. So after refraction from the lens, they the rays are incident on the eye lens, and all are cutting here. So this is the image, inverted image, and from this image for objective lens, it will act as a object for eye lens. It will act as a object for eye lens. So these are the refracted ray. In case of, there are two cases. One is normal adjustment and one is where image form at least distance. So this is the case of normal adjustment. Here image will form at infinity. So when we trace these rays backward, then they come parallel to each other. It means their image will form at infinity. Here, in this case, you have to remember that focal length of objective lens and focal length of eye lens both, in case of in case of in in normal adjustment, both lie at the same place. Focal length of objective and focal length of eye lens both will lie at the same place. Okay, so they both lie at the same place. It means FO plus FE is equal to length of the tube. FO is from here to here and FE is this. Okay, so FO plus FE equals to L, length of the tube. Similarly, we can derive the magnifying power. It is beta by alpha. tan beta upon tan alpha. Tan beta and tan alpha we can write from this triangle. Then magnifying power will be minus FO by FE. Okay, tan beta upon tan alpha. Tan beta and tan alpha we can derive from here. Tan beta from I Fe Pe. From here we can write tan beta and tan alpha from I Fe and Po. From here we can write tan alpha. Okay, so now astronomical telescope, if image format least distance of distinct vision. There is one difference. One is FO and FE here in least distance will not coincide. These will not coincide, and we adjust this so that these ray will not go parallel. These are when we retrace, then these will not go parallel, they will cut here. So here object for objective lens is at infinity and image I is formed at f4. Okay, so this image will act as a object for eyepiece, and this is the final image AB, which will form at the least distance. Similarly, here we will calculate the magnifying power. It is again beta by alpha. It is again beta by alpha. If beta alpha are small, so we can write 10 beta upon 10 alpha. Similarly, 10 beta 10 alpha we can derive from this triangle like we did for normal adjustment case, and this is the formula in this case. Okay, and next is Newtonian telescope. This is reflecting type telescope. Here Newton, this telescope is more effective because here there is no lens, only mirror, so no spherical aberrations are there. So if the ray incident on the mirror parallel to the principal axis, they will reflect. In the path of reflecting light, we put a plane mirror at an angle of 45 degree. So incident ray fall on this mirror and they will reflect. Similarly, this incident ray fall on this mirror and it will reflect. And it will go, this is the eyepiece, it will go in the eye of the observer and a bright image will form, and this magnifying power is FO by FE. This magnifying power is also FO by FE. Okay. So thank you everyone. If you have any doubt, you can ask. Although it is a big chapter, okay, but I try my best. So if you have any problem, then you can ask. Otherwise, you can class.